This video is designed to go with 15.2 in the Musser textbook, and we're talking about systems of equations or solving simultaneous equations. So those are the same thing. You could say systems of equations or simultaneous equations. So what we're going to take a look at is what that even means. And first we're going to take a look at it graphically. So I basically have three different scenarios that can occur with graphs, okay, with lines on a graph. So I could graph a line and then graph a second line that happens to be the exact same line. And I could say that the two lines are identical. So line L is lying directly on top of line M or vice versa. And so every single ordered pair is going to be a solution to this system because they all lie on the line, okay, all together. And so you're going to come to the conclusion that in this case, you're going to have infinite solutions. Then you can have a scenario where you have parallel lines, okay? And we know from previous discussions that parallel lines will never cross, they'll never touch, and in other words, they have the same slope, okay? That's from a previous video. And so what we're saying here is if I call this line L and this line M, will these ever have a point of intersection? Is there going to be a point that is going to satisfy both line L, the equation for line L, and the equation for line M? And the answer would be no, because there is no point that they're going to share. And so in an example like this, if you do it graphically, you will get no solutions. There are no possible scenarios that will simultaneously solve both of those formulas for each of those lines. And then your last possibility, which is the most common, is if you have intersecting lines. If you have intersecting lines, then naturally the point where they intersect is their shared point. So that point will be a solution to both equations, the equation for line L and the equation for line M. And so this ordered pair would be one unique solution for both of them. So this has one solution, which happens to be that intersection point. The bottom line here, though, is that systems of equations have ordered pairs as solutions. So this is not simply solving an algebraic equation and then getting one number and you're done. You would have to actually come up with an ordered pair that satisfies both lines. So the question is, what are we looking for mathematically to see these scenarios come up? So you basically have three ways that you could solve systems of equations. Okay? You could do it graphically, which we just discussed, which means that you could just get each equation into y equals form, and then plot the y-intercepts, and then use the slope to continue plotting points. And if you do it graphically, you will get one of the three solutions to come out. The next way to do it is by substitution. Substitution means that you're going to solve for one of the variables and the way the book does it, they usually do y because everything is just going to be referenced to y, but you do not have to do it based on y. But you're going to solve for one of the variables and then you are literally going to substitute the entire equation, the entire side of one equation in for that variable. In the second equation. And so it literally is a substitution process. And then your last way is called elimination. And again, the name describes exactly what you're going to be doing. You are going to get one of the variables in each equation to be opposite values. Remember from Math 107 that opposite means different signs. And then add the two equations together. So you are only solving, so you only solve for one variable. So next we're going to see how we're going to put these into play. I have the equation x plus y equals 7 and negative 28 equals negative 4x minus 4y. I have a variety of choices that I could do here. If I want to use the elimination process, the first thing I want to do is get them to be in the same form. So I'm going to rewrite the top equation just the opposite way and say 7 equals x plus y. This way, when I write the other equation underneath, all of my variables line up. Now, if I want the letters to be opposite coefficients, these are both negative 4, which means I would have to multiply the entire top equation by positive 4 because I want one of the variables to cancel out. And so that's going to wind up giving me 28 equals 4x plus 4y. And then I'm just going to copy down the other formula directly underneath. And then you add the two formulas together. But what's going to happen here? 28 minus 28 is 0. 4x minus 4x is 0. And 4y minus 4y is 0. And so I wind up getting 0 equals 0. What that means is that these two lines were exactly the same, because if I just took out a negative 1 here, or multiplied this by negative 1, they would be identical. They'd be the exact same line. And we just saw on the previous page that if they're the exact same line, that means that they have infinite solutions. And so mathematically, what's going to happen is that you are going to wind up with a true statement in your algebra. Okay, the fact that 0 equals 0, that is true. And so you wind up with infinite solutions. Okay, let's do one more example. We have 2x plus y equals 5. And we have negative 12 plus 3y equals negative 6x. I want to get the top equation solved for y. And the reason is because I see that it already has a single y in it. So it's easiest just to get y by itself here. So if I do that, I'm going to subtract 2x from both sides. And that's going to give me 5 minus 2x. That means that I can physically substitute 5 minus 2x everywhere I see y. So in the second equation, where I see y, I'm going to substitute this other half of the first equation. So it's going to be negative 12 plus 3 times 5 minus 2x, because again, this is just substituted for y, equals negative 6x. And now it's just a little bit of algebra to work out. So negative 12 plus, they have to distribute this. So 15 minus 6x equals negative 6x. I'm going to have 3 minus 6x equals negative 6x. But now I'm going to go and I'm going to add the 6x to both sides. But I have a problem. That's going to leave me with 3 equals 0. This is not true. This is a false statement. And the question that you need to ask yourself is, will it ever be true? And the answer is no, okay? In our system, in a base 10 system, this is not going to make any sense. And so what we're going to say is that there are no possible solutions. The other way that you could have done this problem is if we got this y by itself, we could do the same thing here. I'm just going to do it along the side. Let's get the second y by itself. The first thing I would do would be to add 12 to both sides. So 3y equals negative 6x plus 12. And then divide everything by 3, and I get y equals negative 2x plus 4. There's something that we need to observe here, and this is from our last video. They both have a slope of negative 2. If two lines have the same slope, then they are parallel. So these two lines are going to be parallel, and they go through two different y-intercepts, because remember, you don't want them to be the same line. Okay, they have to be two different lines because it has to be different from the first example that we did with infinite solutions. So because this has the same slope and different y-intercepts, we know that these two lines are parallel, and so there will be no solutions. So we could say lines are parallel because they have the same slope. And different y-intercepts. And that means that there are no solutions. So that's just another way to prove that that's going to occur. And then finally, you'll have the possibility that there's one specific solution. And let's see what that would look like. We have x plus y equals 7. And then we have 2x plus y equals 5. Because this is nicely set up where the x's and the y's are already lined up, I can easily get one to be the opposite of the other. It doesn't matter which. So because the y's are just single y's, let's just multiply the top one by negative 1, and we'll get the y's to cancel out. So I get negative 1x minus 1y equals negative 7. So all I did was multiply everything by negative 1. And I'm just going to copy the second equation directly below. Now I have negative 1y and y, and so that y is going to disappear. And then if I add these together, I'm going to get x equals negative 2. Now it feels like I'm done because I actually got an x value, but remember, the solutions are ordered pairs. So I'm not done until I plug this value in for x to find y, because you have to get an ordered pair. And so that's the last step that we're going to do. It doesn't matter which equation you use. I'm going to use the first one just because it's simpler. So that means that -2 plus y has to equal 7. And then if I add 2 to both sides, I get y equals 9. And then when I give my answer, I know that it's the ordered pair -2, 9, because it's always going to be an xy value. And that's going to be the solution.